4. Tune SQL queries. Identify and optimize poorly performing SQL queries that contribute to performance bottlenecks. Use query optimization techniques such as query rewriting, index optimization, query hints, and query plan analysis to improve query execution times and resource utilization. 5. Indexing strategies. Use indexes strategically to improve query performance by speeding up data retrieval operations. Identify frequently accessed columns and use indexes to support selective queries and search conditions. Consider the trade-offs between query performance and index maintenance overhead. 6. Database configuration. Configure database parameters, memory allocation, buffer pool size, and cache settings to optimize resource utilization and improve overall system performance. Adjust configuration settings based on workload characteristics, system resources, and performance requirements. 7. Hardware optimization. Optimize hardware resources such as CPU, memory, disk I/O, and to support database operations efficiently. Upgrade hardware components or scale out horizontally to accommodate increasing workloads and demand. 8. Query caching and result set optimization. Implement query caching mechanisms to cache frequently executed queries and result sets in memory, reducing query execution times and database load. Use stored procedures or materialized views to pre-compute and cache complex query results for faster access. 9. Partitioning and sharding. Consider partitioning and sharding strategies to distribute data across multiple physical or logical partitions, improving scalability and parallelism. Partition large tables based on access patterns, data ranges, or key values to distribute workload and optimize query performance. And tune regularly. Continuously monitor database performance metrics, system resources, and workload patterns to identify performance degradation and emerging bottlenecks. Implement proactive performance tuning strategies and conduct regular performance reviews and optimizations. Load testing and capacity planning. Perform load testing and capacity planning exercises to simulate production workloads, identify scalability limits, and ensure that the database system can handle peak demand and growth projections. Scale resources and infrastructure accordingly to accommodate increased workload and user concurrency. 12. Document and documentation. Document performance tuning efforts, optimizations, and best practices for future reference and knowledge sharing. Maintain up-to-date documentation of database configurations, tuning parameters, and performance monitoring procedures. By following these best practices for performance tuning, database administrators can optimize the performance of their database systems, improve user experience, and ensure that the database infrastructure meets the performance requirements and expectations of the organization. Regular monitoring, analysis, and optimization are essential for maintaining optimal performance and responsiveness in dynamic and evolving database environments. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about Database Management System, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to my Advanced Database Management System course. In this section, we discuss about partitioning and sharding, range partitioning, hash partitioning, benefits of partitioning, benefits of sharding. Let's enjoy. Partitioning and sharding are techniques used in distributed database systems to horizontally scale and distribute data across multiple servers or nodes. While both approaches aim to improve database performance and scalability, they have different implementations and use cases. Partitioning. Definition. Partitioning involves dividing a large database table or index into smaller, more manageable segments called partitions. Each partition contains a subset of the data and can be stored on a separate storage device, server, or node. Types of partitioning. Range partitioning. Data is partitioned based on a range of values in a specific column. Example, partitioning by date ranges. Hash partitioning. Data is partitioned based on a hash function applied to a specific column's values. This ensures uniform distribution of data across partitions. List partitioning. Data is partitioned based on predefined lists of values for a specific column. Composite partitioning combines multiple partitioning methods. Example, range and hash partitioning to partition data based on different criteria. Benefits of partitioning. Improved performance. Partitioning allows queries and data retrieval operations to be distributed across multiple partitions, reducing contention and improving query performance. Scalability. Adding new partitions enables horizontal scaling of the database, accommodating larger data volumes and increasing throughput. Manageability. Partitioning facilitates easier management of large datasets by dividing them into smaller, more manageable units. Sharding. Definition. Sharding, also known as horizontal partitioning, involves distributing data across multiple independent database instances or shards. Each shard is responsible for storing a subset of the data, and data distribution is typically based on a sharding key. Key value sharding. In key value sharding, each shard is responsible for keys or values. This ensures that data with similar keys are stored together. Benefits of sharding. Scalability. Sharding enables linear scalability by distributing data and query load across multiple shards. As data volume and query throughput increase, additional shards can be added to handle the load. Fault isolation. Each shard operates independently, providing fault isolation and resilience. A failure in one shard does not affect the availability of other shards. Geographical distribution. Sharding allows data to be distributed geographically across multiple data centers or regions, improving data locality and reducing latency for users in different locations. Comparison. Partitioning, primarily used in single database instances, divides data within a single database, offers improved performance and manageability for large datasets. Sharding, used in distributed database systems, distributes data across multiple independent database instances or shards, enables linear scalability and fault isolation for distributed applications. Thanks for watching the Advanced Database Management System lesson. To learn more about Database Management System, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to Advanced Database. In this section, we discuss about NoSQL types of NoSQL data, document key columns. Definition of NoSQL. Key characteristics: flexible data models, scalability, high availability, distributed architecture. Document stores, key value stores, column family stores, graph databases. Explanation of document-oriented databases. Example: MongoDB features. Explanation of key value databases. Example: Redis features and use cases. Explanation of databases. Example: Aptra features and use cases. Explanation of graph databases. Example: Neo4j features and use cases. Comparison of NoSQL and SQL databases and weaknesses of each approach. Big data applications, real-time analytics, content management systems, IoT data management. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about Database Management System, please check the next lesson. Never enjoy the lesson. Welcome to Advanced Database Management System. In this section, we discuss about NewSQL databases, CockroachDB, key features of NewSQL databases, benefits of NewSQL databases, challenges of NewSQL databases, future trends in NewSQL databases. Let's enjoy. Definition of NewSQL. Characteristics of NewSQL databases. Combines the benefits of traditional SQL databases with scalability and performance as NoSQL, ACID compliance, distributed and horizontally scalable architecture. Overview of CockroachDB features: distributed SQL database, strong consistency, horizontal scalability, multi-active availability. Native representation of relationships, efficient traversal of complex networks, schema flexibility, support for ACID transactions. Combined scalability of NoSQL with ACID compliance SQL, simplified data with CIS, high performance for both read and write operations, horizontal scalability without sacrificing consistency. Data modeling complexity, managing distractions, tuning for distributed queries, operational complexity in managing distributed clusters. Comparison of NewSQL with traditional SQL and NoSQL databases. Use cases where databases offer advantages over other approaches. Advances in distributed query optimization. Integration with cloud-native technologies, example, Kubernetes. Predictions for the future evolution of NewSQL databases. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about Database Management System, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to my Advanced Database Management System course. In this section, we discuss about multi-model databases, multiple data models, unified data management, flexibility and agility, interoperability. Let's enjoy. Multi-model databases are database systems that support multiple data models within a single integrated platform. Unlike traditional databases that are typically designed for a specific data model, e.g., relational, document, graph, multi-model databases offer flexibility and versatility by allowing users to work with different types of data models interchangeably. Here are some key characteristics and considerations of multi-model databases. Support for multiple data models. Multi-model databases support a variety of data models, including relational, document, graph, key value, and time series. This enables users to store and query different types of data using the most appropriate data model for their use case. Unified data management. Multi-model databases provide a unified managing diverse types of data, eliminating the need for separate databases or specialized tools for each data model. This simplifies data management and reduces complexity for developers and administrators. Flexibility and agility. Multi-model databases offer flexibility and agility in data modeling and schema design. Users can choose the most suitable data model for their data and easily adapt to changing requirements without the need for schema migrations or data transformations. Interoperability. Multi-model databases enable seamless interoperability between different data models, allowing users to perform complex queries and analytics that span multiple data types. This promotes integration and facilitates cross-domain analysis and insights generation. Scalability and performance. Multi-model databases are designed to scale horizontally and vertically to handle growing data volumes and user loads. They provide efficient indexing, query optimization, and distributed processing capabilities to ensure high performance and scalability across diverse workloads. Data consistency and integrity. Multi-model databases ensure data consistency and integrity across different data models through transaction support, ACD compliance, and data validation mechanisms. They maintain data consistency constraints and enforce referential integrity to preserve data quality. Use cases. Multi-model databases are well suited for a wide use cases that involve diverse data types and complex data relationships. Examples include content management systems, e-commerce platforms, social networks, IoT data processing, real-time analytics, and fraud detection. Developer. Multi-model databases enhance developer productivity by providing a unified API and query language for accessing and manipulating data across different data models. This reduces the learning curve and allows developers to focus on application logic management with existing systems. Multi-model databases integrate seamlessly with existing systems and data sources, enabling organizations to leverage their existing investments in infrastructure and applications. They support data migration, replication, and synchronization with legacy databases and external data sources. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about database management system, please check the next lesson. Never stop learning. Thanks once again. Lesson. Welcome to my Advanced Database Management System course. In this section, we discuss about monitoring and alerting, monitoring tools, monitor key metrics, implement automated monitoring. Let's enjoy. Monitoring and alerting are essential components of database management, providing insights into system health, performance, and availability. Here are some best practices for monitoring and alerting in database management. 1. Define monitoring objectives. Define clear objectives and goals for monitoring, such as identifying performance bottlenecks, detecting anomalies, ensuring data availability, and meeting service level agreements, SLAs. 2. Select monitoring tools. Choose appropriate monitoring tools and solutions that meet the requirements of your database environment. Consider factors such as scalability, compatibility, features, and ease of use when selecting monitoring tools. 3. Monitor key metrics. Monitor key performance metrics such as CPU utilization, memory usage, disk I/O, network throughput, query latency, transaction throughput, and database connections. Track these metrics over time to identify trends and deviations from normal behavior. 4. Establish baselines. Establish baseline performance metrics for your database system under normal operating conditions. Use historical data and performance benchmarks to define baseline thresholds, deviations from expected performance levels. 5. Implement automated monitoring. Implement automated monitoring solutions that continuously collect and analyze performance data in real time. Use automated monitoring scripts, agents, or monitoring platforms to streamline data collection, analysis, and reporting processes. 6. Set up alerts. Configure alerts and notifications to proactively alert administrators and stakeholders about performance issues anomalies, and potential problems. Set up alert thresholds based on baseline metrics, performance objectives, and criticality of the monitored parameters. 7. Define escalation policies. Define escalation policies and procedures for handling alerts and incidents. Establish clear roles, responsibilities, and escalation paths for responding to alerts, diagnosing problems, and resolving issues in a timely manner. 8. Monitor database logs. Monitor database logs, error logs, and audit logs for warning signs, error messages, and security events. Analyze log data to identify performance bottlenecks, security breaches, and operational issues that require attention. 9. Correlate metrics and events. Correlate performance metrics with system events, database activities, and workload patterns to gain deeper insights into performance trends and root causes of issues. Use correlation analysis to identify cause and effect relationships between different metrics and events. Conduct capacity planning. Use monitoring data and performance trends to conduct capacity planning and resource allocation. Forecast future capacity requirements based on growth projections, workload patterns, and performance trends to ensure scalability and optimal resource utilization. Regularly review and tune alerts. Regularly review alerting configurations, alert thresholds, and alerting rules to ensure that they remain relevant and effective. Fine-tune alerting parameters based on feedback, changes in workload, and evolving business requirements. 12. Document monitoring procedures. Document monitoring procedures, alerting configurations, and incident response workflows for reference and knowledge sharing. Maintain up-to-date documentation of monitoring tools, metrics, alerts, and escalation procedures. By following these best practices for monitoring and alerting, database administrators can proactively detect, diagnose, and resolve performance issues, ensure data availability, and maintain the health and reliability of their database systems. Continuous monitoring, analysis, and optimization are essential for effectively managing database environments and meeting the performance objectives of the organization. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about Database Management System, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to my Advanced Database Management System course. In this section, we discuss about machine learning and AI in databases, natural language processing, NLP, data security and privacy, automated insights and data exploration. Let's enjoy. Machine learning, ML, and artificial intelligence, AI, are increasingly being integrated into databases to enhance their capabilities and provide more intelligent data management and analytics solutions. Here are some ways ML and AI are used in databases. Query optimization. ML algorithms can analyze query patterns and historical query execution data to optimize query performance. By learning from past query executions, ML models can suggest better query plans, indexing strategies, and database configurations to improve overall system performance. Recommendation systems. AI algorithms such as collaborative filtering and content-based filtering are used to build recommendation systems in databases. These systems analyze user behavior and preferences stored in the database to generate personalized recommendations for products, services, or content. Natural language processing NLP techniques enable databases to understand and process natural language queries and commands. By incorporating NLP capabilities, databases can support voice search, conversational interfaces, and text-based query processing, making data access more intuitive and user-friendly. Automated data management. AI-driven automation tools can assist in data management tasks such as data cleaning, data integration, and data categorization. ML algorithms can learn from historical data management activities to automate repetitive tasks and improve data quality and consistency. Data security and privacy. ML and AI techniques are used to enhance data security and privacy in databases. AI-powered systems can analyze patterns and user behavior to detect potential security threats and anomalies. Additionally, NL models can help in data anonymization, encryption, and compliance with privacy regulations such as GDPR. Optimized resource allocation. ML algorithms can analyze resource usage patterns in databases and predict future resource requirements. By optimizing resource allocation, databases can ensure efficient utilization of computing resources such as CPU, memory, and storage, leading to cost savings and improved performance. Automated insights and data exploration. AI-driven data exploration tools can analyze large data sets stored in databases and automatically generate insights, trends, and patterns. These tools enable users to uncover hidden insights and make data-driven decisions without requiring extensive manual analysis. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about Database Management System, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to Advanced Database Management System. In this section, we discuss about key value stores. Redis. Key features of key value stores. Benefits of key value stores. Best practices for working with key value stores. Future trends in key value stores. Let's enjoy. Definition of key value stores. Characteristics of key value databases. Basic data model. Pairs of keys and associated values. Simplicity and scalability and fault tolerance. Overview of Redis data model in Redis. Key value pairs. Features. In-memory data storage. Support for various data types. Strings, lists, sets, etc. Pub-sub messaging. Built-in replication and clustering. Simple data model. Keys mapped to values. High performance for read and write operations. In-memory and disk-based storage options. Support for data types beyond strings, e.g. lists, sets, hashes. High performance and low latency. Scalability for handling large datasets. Simple data model and ease of use. Versatility in supporting various use cases. Comparison of key value and relational data models. When to choose a key value store over a relational database. Choosing appropriate data structures for keys and values. Optimizing cache eviction policies. Handling data persistence and backups. Monitoring and performance tuning. Advances in in-memory computing technologies. Integration with other data processing frameworks, e.g. Apache Spark. Predictions for the future of key value databases. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about Database Management System, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to Advanced Database Management System. In this section, we discuss about join operations, types of joins, inner join, left join, right join, full join, cross join. Let's enjoy. Join operations in SQL. Join operations allow you to retrieve data from multiple related tables based on a related column. Same types of joins. Inner join returns only rows that have matching values in both tables. Select e.name, d.department name from employees E, inner join departments D on eDepartment ID equals DID. Left join or left outer join returns all rows from the left table and matched rows from the right table. Unmatched rows from the right will have null. Select ename D department name from employees E left join departments D on eDepartment ID equals DID. Right join or right outer join returns all rows from the right table and matched rows from the left table. Select E.name D department name from employees E right join departments D on eDepartment ID equals D.ID. Full join or full outer join returns all rows when there is a match in one of the tables. SQL select E.name D department name from employees E full join departments D on eDepartment ID equals D.ID. Cross-join returns the Cartesian product of both tables, every combination. Select E name P project name from employees E cross-join projects P. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about Database Management System, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to my Advanced Database Management System course. In this section, we discuss about isolation levels, read uncommitted, read committed, repeatable read, serializable. Let's enjoy. Isolation levels define the degree to which the transactions in a database system are isolated from each other. Different isolation levels provide different trade-offs between data consistency and concurrency. The commonly used isolation levels are defined by the SQL standard. They include read uncommitted. In the read uncommitted isolation level, transactions are not isolated from each other. This means that a transaction can see uncommitted changes made by other transactions. Read uncommitted provides the highest degree of concurrency, but sacrifices data consistency, since transactions can read dirty data, data that has not been committed yet. Read committed. In the read committed isolation level, transactions can only see committed data. This means that a transaction cannot read data that has been modified but not yet committed by other transactions. Read committed isolation level prevents dirty reads but allows non-repeatable reads and phantom reads. Repeatable read. In the repeatable read isolation level, a transaction sees a consistent snapshot of the database at the time the transaction starts. This means that any data transaction remain unchanged during the transaction's lifetime, even if other transactions modify or delete the data. Repeatable read prevents dirty reads and non-repeatable reads, but allows phantom reads. Serializable. In the serializable isolation level, transactions are completely isolated from each other. This means that transactions execute as if they were the only transactions running on the database. Serializable provides the highest level of data consistency, but can lead to decreased concurrency and increased contention due to locking. Snapshot isolation. Snapshot isolation is a variation of the repeatable read isolation level that provides a consistent snapshot of the database at the time the transaction starts. However, unlike repeatable read, snapshot isolation allows other transactions to modify the data concurrently. Each transaction sees a consistent snapshot of the database, but it may see different versions of the data modified by other transactions. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about Database Management System, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to my Advanced Database Management System course. In this section, we discuss about indexing and query optimization, types of indexes, benefits of indexing, query optimization techniques for query optimization. Let's enjoy. Indexing and query optimization are essential techniques used to improve the performance of database systems by speeding up data retrieval and query processing. Here's an overview of indexing and query optimization. Indexing. What is an index? An index is a data structure associated with a database table that allows for efficient retrieval of data based on certain columns or expressions. Indexes provide a quick lookup mechanism, similar to the index of a book, allowing the database to locate specific rows quickly without scanning the entire table. Types of indexes. B-tree index, the most common type of index used in database systems. It stores keys in sorted order, allowing for efficient range queries and equality searches. Hash index uses a hash function to map keys to index entries, providing constant time lookup for equality searches but not supporting range queries. Bitmap index, suitable for columns with low cardinality, where each bit in the index represents the presence or absence of a value. Full text index, designed for efficient text searches, supporting operations such as word searches and phrase searches. Spatial index, optimized for spatial data types, enabling efficient retrieval of spatial objects based on their geometric properties. Creating indexes. Indexes can be created using SQL commands, such as create index. You specify the table and column S to be indexed, and the database system creates the index accordingly. Benefits of indexing. Improved query performance. Indexes speed up data retrieval operations, especially for columns frequently used in search conditions or join predicates. Enhanced data integrity. Unique indexes enforce uniqueness constraints, preventing duplicate values in indexed columns. Support for constraints. Indexes can be used to enforce primary key, unique key, and foreign key constraints. What is query optimization? Query optimization is the process of improving the performance of database queries by selecting efficient execution plans. The goal is to minimize query execution time, reduce resource consumption, and improve overall system efficiency. Query execution plans. A query execution plan is a sequence of operations performed by the database system to retrieve and process data requested by a query. The optimizer generates multiple execution plans and selects the one with the lowest cost based on factors such as access methods, join algorithms, and index usage. Techniques for query optimization. Cost-based optimization uses statistical information and cost models to estimate the cost of executing different query plans and selects the plan with the lowest estimated cost. Query rewriting transforms the original query into an equivalent form that can be executed more efficiently. Techniques include predicate pushdown, join reordering, and subquery optimization. Index usage identifies and selects appropriate indexes to access data efficiently. The optimizer considers index selectivity and access path options. For example, index scans, index seeks. Join optimization determines the most efficient join order and join algorithms. For example, nested loop join, hash join, merge join, based on the size of the tables, join conditions, and available indexes. Parallel execution executes queries in parallel across multiple CPU cores or nodes to exploit parallelism and reduce query execution time. Monitoring and tuning. Query performance should be regularly monitored using tools such as database performance monitors and profiler tools. Performance bottlenecks can be identified and query optimization techniques can be applied to address them. This includes creating or modifying indexes, rewriting queries, or adjusting database configuration parameters. Effective indexing and query optimization play a crucial role in database performance, reducing query response times and enhancing overall system scalability and efficiency. By utilizing appropriate indexing strategies and optimizing query execution plans, database administrators can ensure optimal performance and responsiveness of their database systems. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about Database Management System, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to Advanced Database Management System. In this section, we discuss the database's implementation considerations, challenges and limitations, future trends. Let's enjoy. Overview of the architecture, data storage in main memory, mechanisms for durability persistence, snapshots, transaction logging, replication, memory requirements, data persistence strategies, scalability options, integration with existing systems, memory requirements, data persistence strategies, options, integration with existing systems, memory constraints, cost considerations, data persistence complexities, integration challenges with existing infrastructure, continued growth of bases in technology, for example, non-volatile memory, integration with emerging, for example, edge computing. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about Database Management System, please check the next lesson. Never stop. Thanks once again to enjoy the lesson. Welcome to my Advanced Database Management System course. In this section, we discuss about edge computing databases, proximity to data sources, low latency processing, offline operation, distributed architecture, resource efficiency. Let's enjoy. Edge computing databases are database systems specifically designed to operate at the edge of the network, closer to the data sources and end users. These databases are optimized for low latency, high throughput data processing, and storage in edge computing environments. Here are some statistics and considerations of edge computing databases. Proximity to data sources. Edge computing databases are deployed closer to the data sources, such as IoT devices, sensors, and edge servers. This proximity reduces latency and network bandwidth usage by processing and storing data locally at the edge. Low latency processing. Edge computing databases prioritize low latency data processing to support real-time applications and services at the edge. They minimize data round-trip times and response times by executing data processing tasks locally without relying on centralized cloud servers. Offline operation. Edge computing databases are designed to operate offline or with intermittent connectivity, as edge environments may experience network disruptions or limited connectivity. They provide mechanisms for local data caching and synchronization to ensure data availability and continuity of service. Distributed architecture. Edge computing databases employ distributed architectures that span multiple edge nodes or devices. They support data replication, synchronization, and consistency mechanisms to maintain data integrity and availability across distributed edge environments. Resource efficiency. Edge computing databases are optimized for resource-constrained edge devices with limited compute, memory, and storage capabilities. They minimize resource usage by employing lightweight data storage formats, efficient indexing structures, and data compression techniques. Edge analytics. Databases support real-time analytics and data processing at the edge, enabling edge devices to analyze and act on data locally without the need to transmit data to centralized servers. This enables faster decision-making and reduces reliance on cloud-based analytics. Security and privacy. Edge computing databases implement robust security features to protect data at the edge, including encryption, access controls, authentication, and data anonymization. They ensure data privacy and compliance with regulatory requirements, such as GDPR and HIPAA, in edge computing environments. Integration with cloud services. Edge computing databases seamlessly integrate with cloud services and centralized data platforms, enabling hybrid cloud edge deployments. They support data synchronization, replication, and streaming between edge devices and cloud-based databases for centralized data analysis and storage. Edge cloud orchestration. Edge computing databases work in conjunction with edge cloud orchestration platforms, such as Kubernetes or Docker Swarm, to manage and orchestrate edge computing resources. They support containerized deployments and microservices architectures for scalable and flexible edge deployments. Thanks for watching the Advanced Database Management. Hope you enjoy the lesson. To learn more about Database Management System, please check the next lesson. Thanks once again to enjoy the lesson. Welcome to Advanced Database Management System. In this section, we discuss about graph databases, Neo4j benefits of graph databases, key features of graph databases, best practices for working with graph databases, future trends in graph databases. Let's enjoy. Definition of graph databases, characteristics of graph databases, data represented as nodes, edges, and properties, optimized for traversing relationships, use cases, social networks, recommendation engines, fraud detection. Introduction to Neo4j, data model in Neo4j. Nodes, relationships, properties, features, native graph storage and processing, query language, ACID compliance, high availability clustering, native representation of relationships, efficient traversal of complex networks, schema flexibility, support for ACID transactions, natural representation of connected data, high performance for relationship-heavy queries, flexible schema evolution, powerful graph algorithms and analytics, comparison of graph and relational data models, use cases where graph databases excel over relational databases, effective data modeling strategies for graph structures, optimizing queries and indexes, cluster configuration and optimization, monitoring and maintenance practices, advances in graph algorithms and analytics, integration with machine learning and AI technologies, predictions for the future evolution of graph databases. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about Database Management System, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to my Advanced Database Management System course. In this section, we discuss about popular NoSQL DBMS, MongoDB, Cassandra, Redis, Elasticsearch, Apache HBase, Amazon DynamoDB, Couchbase, Neo4j. Let's enjoy. NoSQL databases, also known as not only SQL databases, are designed to handle large volumes of unstructured or semi-structured data and offer flexible data models and horizontal scalability. Here are some of the most popular NoSQL database management systems, DBMS. MongoDB. MongoDB is a document-oriented NoSQL database that stores data in flexible, JSON-like documents. It is known for its scalability, high performance, and ease of use. MongoDB is commonly used in web applications, content management systems, and real-time analytics. Cassandra. Apache Cassandra is a distributed NoSQL database designed for high availability and linear scalability. It is optimized for handling large amounts of data across multiple nodes in a distributed cluster. Cassandra is widely used in applications requiring high write throughput and fault tolerance, such as social media platforms and Internet of Things (IoT) systems. Redis is an in-memory data store that supports various data structures, including strings, hashes, lists, sets, and sorted sets. It is known for its high performance and low latency, making it suitable for caching, session management, and real-time analytics. Redis is often used in web applications, gaming, and message queuing systems. Elasticsearch. Elasticsearch is a distributed search and analytics engine based on the Lucene library. It is designed for full-text search, log analytics, and real-time data analysis. Elasticsearch is commonly used in applications requiring fast and scalable search capabilities, such as e-commerce platforms, log management systems, and monitoring solutions. Apache HBase. Apache HBase is a distributed columnar database that runs on top of the Hadoop Distributed File System, HDFS. It is designed for random, real-time read-write access to large datasets. HBase is commonly used in big data analytics, time series data storage, and real-time event processing. Amazon DynamoDB. DynamoDB is a fully managed NoSQL database service provided by Amazon Web Services, AWS. It offers high availability, durability, and scalability with low latency performance. DynamoDB is commonly used in cloud-native applications, gaming, and Internet of Things (IoT) solutions. Couchbase. Couchbase is a distributed NoSQL database that combines the flexibility of a document database with the performance of a key value store. It supports SQL-like queries, distributed transactions, and built-in caching. Couchbase is often used in applications requiring high availability, low latency, and real-time analytics. Neo4j. Neo4j is a graph database that stores data in nodes and relationships, allowing for efficient traversal of complex relationships between entities. It is commonly used in social networks, recommendation engines, and fraud detection systems. These are some of the most popular NoSQL databases, each offering unique features and capabilities to address different use cases and requirements. The choice of NoSQL database depends on factors such as data volume, complexity, performance requirements, and scalability needs. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about Database Management System, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to my Advanced Database Management System course. In this section, we discuss about transaction management, transaction states, transaction, commit, rollback, and save point. Let's enjoy. Transaction management is a crucial aspect of database systems that involves the management and control of database transactions to ensure their atomicity, consistency, isolation, and durability, ACID properties. Here are the key components and concepts related to transaction management. Transaction. A transaction is a logical unit of work that consists of one or more database operations, such as inserts, updates, deletes, that are executed as a single unit. Transactions are typically initiated by applications and are executed by the Database Management System, DBMS. ACID properties. Transactions must adhere to the ACID properties to ensure their reliability and consistency. Atomicity ensures that transactions are either fully completed or fully rolled back if an error occurs. Consistency ensures that the database remains in a valid state before and after the transaction. Isolation ensures that transactions execute independently of each other. Transaction states. Transactions typically progress through several states during their life cycle, including active, partially committed, committed, and aborted. In the active state, a transaction is executing its operations. Successful completion, it enters the partially committed state before finally committing its changes to the database. Transaction control statements. DBNS provide transaction control statements to manage transactions effectively. These include begin transaction, commit, rollback, and save point. Begin transaction marks the start of a transaction. Commit saves the changes made by the transaction to the database. Rollback undoes the changes made by the transaction and restores the database to its original state. Save point creates a point within the transaction you can later roll back. Concurrency control. Concurrency control mechanisms ensure that transactions execute concurrently while maintaining data consistency and isolation. Techniques such as locking, optimistic concurrency control, and multi-version concurrency control, MVCC, are used to manage concurrent access to shared resources and prevent data corruption or inconsistencies. Transaction isolation levels. Transaction isolation levels define the degree of isolation between concurrent transactions. Common isolation levels include read uncommitted, read committed, repeatable read, and serializable. Each isolation level provides a different trade-off between data consistency and concurrency. Transaction logging. Transaction logging is the process of recording all changes made by transactions in a log file before they are applied to the database. Transaction logs are used for crash recovery, rollbacks, and maintaining durability. They ensure that changes made by committed transactions can be replayed in case of system failures. Save points. Save points are markers within a transaction that allow you to create named points to which you can later roll back. Save points provide a way to create intermediate rollback points within a transaction, allowing you to undo changes made up to a specific point without rolling back the entire transaction. Distributed transactions. In distributed database environments, transactions may span multiple database systems or nodes. Distributed transaction management ensures that transactions across multiple databases maintain ACID properties even in a distributed environment. Techniques such as two-phase commit, 2PC, and distributed locking are used to coordinate distributed transactions. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about Database Management System, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to my Advanced Database Management System course. In this section, we discussed about time series and IoT databases, time series data model, compression, and downsampling, data retention policies, support for complex queries. Let's enjoy. Time series and IoT databases are database systems efficiently store, manage time-stamped data by IoT, Internet of Things, devices. These databases are optimized for handling large volumes of time series data, which typically consist of measurements, events, and observations collected at regular intervals over time. Here are some key characteristics and considerations of time series and IoT databases. Time series data model. Time series databases organize data based on timestamps, with each data point associated with a specific timestamp indicating when the measurement or event occurred. This data model allows for efficient storage and analysis of timestamped data. Time series and IoT databases are optimized for high throughput and low latency, enabling real-time ingestion and processing of streaming data from IoT devices and sensors. They support fast data ingestion rates and sub-second query response times to support real-time analytics and monitoring applications. compression and downsampling. Time series databases employ compression and downsampling techniques to reduce storage requirements and optimize query performance for time series data. They aggregate and summarize data at different granularities, for example, minute, hour, day, to maintain data fidelity while conserving storage space. Scalability and horizontal partitioning. Time series and IoT databases are designed to scale horizontally to accommodate growing data volumes and user loads. They partition data across multiple nodes or shards, enabling parallel processing and distributed storage to handle large-scale deployments. Data retention policies. Time series databases support configurable data retention policies that specify how long data should be retained in the database before being automatically purged or archived. This helps manage storage costs and ensures compliance with data retention regulations. Support for complex queries. Time series and IoT databases provide specialized query languages and APIs for querying and analyzing time series data. They support a wide range of analytical functions, aggregations, and transformations for extracting insights from time-stamped data. Integration with streaming platforms. Time series and IoT databases integrate with streaming data platforms, such as Apache Kafka or AWS Kinesis, to ingest, process, and analyze real-time data streams from IoT devices and sensors. They support seamless integration with streaming analytics frameworks for continuous data processing. Data visualization and dashboarding. Time series and IoTs often include built-in data visualization tools and dashboarding capabilities to visualize time series data in real time. They support interactive charts, graphs, and dashboards for monitoring and analyzing IoT data streams. Edge computing support. Time series and IoT are compatible with edge computing environments, allowing them to be deployed closer to IoT devices and sensors for local data processing and analysis. They support lightweight deployment options and edge-native architectures to minimize latency and network bandwidth usage. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about database management system, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to Advanced Database Management System. In this section, we discuss about time series databases, characteristics of time series data, why time series databases, how time series databases work, future trends. Let's enjoy. Time series databases. Sequential nature, timestamps, regular intervals, and velocity. Examples of time series data, such as sensor data, financial data, IoT data. Traditional databases versus time series databases. Key advantages: optimized storage and retrieval, efficient time-based queries, scalability for large volumes of data, support for real-time analytics, specialized data modeling for time series data. Overview of architecture. Data model for time series data. Storage optimization techniques, e.g., downsampling, compression. Querying and analysis capabilities. Continued growth. Data. Advances in time series database technology. Integration with machine learning and AI for predictive analytics. Use of time series data in edge computing and IoT. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about database management system, please check the next lesson. Never stop to enjoy the lesson. Welcome to my Advanced Database course. In this section, we discuss about stored procedures and functions, advantages, usage. Let's enjoy. Stored procedures and functions are two types of database objects that encapsulate a set of SQL statements and can be executed by invoking their names. They are commonly used in databases to perform repetitive tasks, implement business logic, and enhance application performance. Here's an overview of stored procedures and functions. Stored procedures. Definition. A stored procedure is a named set of SQL statements stored in the database catalog. Advantages. Encapsulate complex logic. Enhance security by controlling access to database objects. Improve performance by reducing network traffic, especially in client-server architectures. Functions. Definition. A function is a named set of SQL statements that returns a single value. Functions can be deterministic or non-deterministic. They can be scalar functions, returning a single value, or table-valued functions, returning a table. Creation. Functions are created using the create function statement. They are written in SQL or in a procedural language supported by the database system. Advantages. Promote code reusability. Allow computations within queries. Improve maintainability by separating logic from SQL query. Differences. Return type. Stored procedures do not have a return type, while functions must return a single value or a table. Usage. Stored procedures are used to perform operations and may or may not return values. Functions are primarily used for computations and always can contain transactional control statements, e.g. commit, rollback, while functions cannot. Access. Stored procedures can perform DML operations, insert, update, delete, on tables. Functions are typically used for read-only operations and cannot modify data in tables. Both stored procedures and functions are essential tools in database development, offering a convenient way to modularize and reuse code while improving performance and maintainability. Choosing between them depends on the specific requirements of your application and the type of task you need to accomplish. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about Database Management System, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to Advanced Database Management System. In this section, we discuss about spatial databases, characteristics of spatial data, why spatial databases, popular spatial databases, future trends. Let's enjoy. Spatial databases. Location-based information. Representation of geometric objects, points, lines, polygons. Spatial relationships. Example, distance, containment. Temporal aspects in spatial data. Challenges with handling spatial data in traditional databases. Key advantages of spatial databases. Optimized storage and retrieval of spatial data. Efficient spatial queries and analysis. Support for spatial indexing and spatial functions. Integration with GIS applications and tools. PostGIS, Oracle Spatial, MongoDB Spatialite, Microsoft SQL Server. Growing importance of location-based insights in various industries. Advances in spatial database technology, e.g., support for 3D spatial data. Integration with IoT and sensor networks for real-time spatial data. Use of spatial data in machine learning and AI applications. The Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about Database Management System, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to my Advanced Database Management System course. In this section, we discuss about spatial and graph databases, spatial data types, spatial indexing, spatial query operations, graph databases. Let's enjoy. Spatial and graph databases are specialized database systems designed to handle specific types of data and relationships. Here's an overview of each. Spatial databases. Definition. Spatial databases are optimized for storing and querying spatial data, such as geographic information systems, GIS data, maps, and location-based data. They support spatial data types, spatial indexing, and spatial query operations to efficiently manage and analyze spatial data. Spatial data types. Spatial databases support spatial data types such as points, lines, polygons, and geometries to represent geographic features and spatial relationships. These data types enable the storage and manipulation of spatial data in a structured format. Spatial indexing. Spatial databases use spatial indexing techniques such as R-tree or quad-tree indexes to accelerate spatial query processing and improve query performance. Spatial indexes organize spatial data in a hierarchical structure to efficiently retrieve data based on spatial proximity and relationships. Spatial query operations. Spatial databases support spatial query operations, including point and polygon tests, nearest neighbor searches, spatial joins, and spatial analysis functions. These operations enable users to perform complex spatial analyses and derive insights from spatial data. Use cases. Spatial databases are used in various applications and industries that deal with spatial data, including GIS applications, location-based services, urban planning, environmental monitoring, transportation and logistics, real estate, and natural resource management. Examples: popular spatial database PostGIS extension for and graph, Microsoft SQL Spatial, MongoDB with GeoJSON support, and Elasticsearch with GeoQueries. Graph databases. Definition. Graph databases are designed to store and query graph data structures consisting of nodes, edges, and properties. They model complex relationships between entities and support graph query languages and algorithms for analyzing graph data. Graph data model. Graph databases represent data as a graph, where nodes represent entities, e.g., people, products, locations, and edges represent relationships between entities. Nodes and edges can have properties or attributes that provide additional information about the entities and relations. Graph query languages. Graph databases support graph query languages, such as Cypher, used in Neo4j, Gremlin, used in Apache Tinkerpop, and Sparkle, used in RDF databases, for expressing graph patterns and traversing relationships in the graph. Graph algorithms. Graph databases provide built-in graph algorithms and analytics for performing tasks such as path finding, centrality analysis, community detection, and graph clustering. These algorithms enable users to gain insights from complex graph structures and relationships. Use cases. Graph databases are used in various applications and domains that involve analyzing and visualizing complex relationships, including social networks, recommendation systems, fraud detection, network and IT operations, knowledge graphs, and bioinformatics. Examples. Popular graph databases include Neo4j, Amazon Neptune, Janus Graph, OrangoDB, TigerGraph, and dgraph. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about Database Management System, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to my Advanced Database Management System course. In this section, we discuss about serverless databases, no server management, automatic scaling, event-driven architecture, managed services. Let's enjoy. Serverless databases are a type of database service that abstracts away the underlying infrastructure management, allowing developers to focus solely on building and accessing their databases without dealing with server provisioning, scaling, or maintenance. Here are some key characteristics and considerations of serverless databases. No server management. Serverless databases, developers do not need to provision or manage database servers. The cloud provider handles server provisioning, scaling, patching, and maintenance tasks, freeing developers from infrastructure management responsibilities. Automatic scaling. Serverless databases automatically scale resources up or down based on demand. They can handle fluctuating workloads and spikes in traffic without manual intervention, ensuring optimal performance and cost efficiency. Pay-per-use billing. Serverless databases follow a pay-per-use billing model, where users are charged based on actual resource consumption, e.g. storage, compute, and data transfer, rather than pre-provisioned capacity. This allows organizations to align costs with usage and avoid over-provisioning. Event-driven architecture. Serverless databases are well suited for event-driven architectures and serverless computing platforms, such as AWS Lambda or Azure Functions. They can integrate seamlessly with serverless applications, responding to database events and triggers in real time. Managed services. Serverless databases are fully managed by the cloud provider, offering managed services for database provisioning, configuration, monitoring, backups, and security. This offloads administrative tasks from developers, allowing them to focus on application development. Automatic backup and recovery. Serverless databases automatically perform backups and maintain multiple copies of data to ensure data durability and availability. They offer built-in backup and recovery features, allowing users to restore data to a specific point in time if needed. High availability and reliability. Serverless databases are designed for high availability and reliability, with built-in redundancy, failover mechanisms, and data replication across multiple availability zones or regions. This ensures continuous access to data and minimizes downtime. Security and compliance. Serverless databases implement robust security features, such as encryption at rest and in transit, access controls, audit logging, and compliance certifications, e.g. SOC 2, HIPAA. They provide a secure environment for storing and accessing sensitive data. Vendor lock-in. While serverless databases offer convenience and scalability, they may also lead to vendor lock-in, as developers become reliant on the proprietary features and APIs provided by the cloud provider. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about Database Management System, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to my Advanced Database Management System course. In this section, we discuss about scaling and high availability, vertical scaling, horizontal scaling, load balancing, replication, clustering. Let's enjoy. Scaling and high availability are critical considerations in database management, especially for applications with growing user bases, increasing workloads, and demanding performance requirements. Here are some best practices for scaling and achieving high availability in database management. 1. Vertical scaling. Vertical scaling involves adding more resources, CPU, memory, storage to a single server to handle increased workload. Upgrade hardware components, provision engines to support growing database requirements. While versioning can provide immediate performance improvements, it may have limitations in terms of scalability and cost effectiveness. 2. Horizontal scaling. Horizontal scaling involves distributing database load across multiple servers or instances to handle increased traffic and workload. Implement sharding, partitioning, or replication techniques to distribute data and transactions across multiple nodes. Horizontal scaling offers better scalability and fault tolerance, but requires careful planning and coordination. Use load balancing techniques to evenly distribute incoming traffic and workload across multiple database servers or replicas. Implement load balancers, proxies, or application-level load balancing to optimize resource utilization and improve system performance. Replication. Implement database replication to create copies, replicas, of the database on multiple servers. Use synchronous or asynchronous replication to replicate data changes from the primary database to replica databases. Replication improves fault tolerance, data availability, and read scalability. 5. Clustering. Deploy database clusters or cluster management solutions to create a group of interconnected database nodes that work together to provide high availability and scalability. Use clustering technologies such as MySQL cluster, PostgreSQL cluster, or Oracle RAC, real application clusters, to achieve fault tolerance and load distribution. 6. Data partitioning, sharding. Partition large datasets into smaller subsets, shards, based on predefined criteria such as key ranges, geographic regions, or user demographics. Distribute data shards across multiple database nodes to achieve horizontal scalability and improve query performance. 7. Replication lag monitoring. Monitor replication lag between primary and replica databases to ensure data consistency and minimize replication delays. Implement monitoring tools and alerting mechanisms to detect and troubleshoot replication lag issues in real time. 8. Disaster recovery, DR. Implement disaster recovery, DR strategies and solutions to ensure business continuity and data resilience in the event of hardware failures, natural disasters, or human errors. Establish off-site backups, data replication, and failover procedures to minimize downtime and data loss. 9. Automated failover. Configure automated failover mechanisms to detect database failures and automatically switch traffic to standby nodes or replicas. Implement health checks, heartbeat monitoring, and automated failover scripts to ensure fast and seamless failover in case of node or server failures. 10. Multi-region deployment. Deploy database instances across multiple geographic regions or availability zones to improve fault tolerance, disaster recovery, and data locality. Use cloud-based database services that offer multi-region deployment options for improved high availability and scalability. 11. Performance testing and optimization. Conduct performance testing and optimization exercises to identify performance bottlenecks, scalability limits, and optimization opportunities. Test database scalability under simulated production workloads and adjust configurations, indexes, and queries for optimal performance. 12. Regular maintenance and monitoring. Perform regular maintenance tasks such as database backups, software updates, and performance tuning to ensure the health and reliability of the database infrastructure. Monitor database performance metrics, replication status, and cluster health to proactively detect and resolve issues. By following these best practices for scaling and achieving high availability in database management, organizations can ensure that their database systems can accommodate growing workloads, maintain data availability, and meet performance objectives, even under demanding conditions. Continuous monitoring, testing, and optimization are essential for maintaining the scalability, reliability, and performance of the database infrastructure over time. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about Database Management System, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to my Advanced Database Management System course. In this section, we discuss about role-based access control, RBAC permissions, role assignment, separation of duties, SOD, policy enforcement, database-level encryption. Let's enjoy. Role-based access control, RBAC, is a widely used access control mechanism that restricts system access to authorized users based on their roles within an organization. In RBAC, permissions are assigned to roles, and users are assigned to one or more roles. Users inherit the permissions associated with their assigned roles, simplifying access management and enforcing the principle of least privilege. Here's an overview of RBAC. 1. Roles. A role is a collection of permissions that define a set of actions or operations that users with that role are allowed to perform. Roles are typically defined based on job responsibilities, organizational hierarchical requirements. Examples of roles include admin, manager, employee, etc. 2. Permissions. Permissions are rules or privileges that specify what actions a user with a particular role is allowed to perform within a system or application. Permissions can be granular and may include read, write, update, delete, execute, or administrative privileges for specific resources or functionalities. 3. Users. Users are individuals or entities granted access to a system or application. Each user is assigned one or more roles, which determine their access rights and privileges within the system. Users can be assigned to roles manually by administrators or dynamically, based on attributes such as job title or department membership. 4. Role assignment. Role assignment involves associating users with roles to define their access permissions within a system. Users may be assigned to roles based on their job responsibilities, functional requirements, or organizational hierarchy. Role assignment can be performed manually by administrators. 5. Role hierarchy. RBAC systems may support role hierarchies, where roles are organized into parent-child relationships. Users assigned to a parent role inherit the permissions of all child roles within the hierarchy. Role hierarchies help streamline access management. 6. Separation of duties, SOD. RBAC systems often enforce separation of duties, which prevents conflicts of interest and reduces the risk of fraud or misuse. SOD policies restrict users from being assigned to conflicting roles that would allow them to perform incompatible actions or operations within the system. 7. Policy enforcement. RBAC policies are enforced by the system's access control mechanisms, which validate user requests against their assigned roles and permissions. Access control lists, ACLs, role mappings, and authorization rules are used to determine whether a user is authorized to perform a specific action or access a particular resource. 7. Database-level encryption. Some DBMSs offer database-level encryption features that allow users to encrypt entire databases or specific columns within tables. This provides granular control over which data is encrypted and helps minimize performance overhead. 8. Application-level encryption. In addition to database-level encryption, applications can implement encryption mechanisms to protect sensitive data before it is stored in the database. This approach provides an additional layer of security and allows applications to enforce business-specific encryption requirements. 9. Benefits of RBAC. RBAC offers several benefits, including simplified access management. Roles encapsulate sets of permissions, making it easier to manage user access and permissions at scale. Granular control. RBAC allows administrators to define fine-grained permissions for different roles and resources, ensuring that users have access only to the information and functionality they need to perform their job duties. Improved security. RBAC reduces the risk of unauthorized access and data breaches by enforcing the principle of least privilege and restricting users to only the permissions necessary to perform their assigned tasks. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about Database Management System, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to my Advanced Database Management System course. In this section, we discuss about replication and clustering, types of replication, benefits of replication, types of clustering, benefits of clustering. Let's enjoy. Replication and clustering are two common techniques used in database systems to improve fault tolerance. While both approaches aim to enhance system reliability and scalability, they have distinct implementations and use cases. Replication. Definition. Replication involves creating and maintaining multiple copies of the same data across multiple servers or nodes. These copies, known as replicas, are synchronized to ensure consistency and can be used for read operations to distribute the query load. Types of replication. Master-slave replication. In this setup, one database server acts as the master, handling both read and write operations. Replicas, or slaves, replicate data from the master and serve read-only queries. Write operations are forwarded to the master. Master-master replication. In this configuration, multiple database servers act as both master and slave, allowing read and write operations on any node. Benefits of replication. High availability. Replication provides redundancy by maintaining multiple copies of data. If one server fails, clients can switch to another replica, ensuring continuous service availability. Fault tolerance. Replication improves fault tolerance by ensuring that data remains accessible even if one or more servers fail. Load balancing. Read-heavy workloads can be distributed among replicas, reducing the query load. Clustering. Clustering involves grouping multiple database servers together to work as a single logical unit. Clustered servers share resources, such as storage and memory, and collaborate to handle client requests. Types of clustering. Failover clustering. In failover clustering, multiple servers are grouped together to provide high availability. If one server fails, another server in the cluster automatically takes over its workload without interruption. Load balancing clustering. Load balancing clustering distributes client requests among multiple servers in the cluster, ensuring optimal resource utilization and performance. Shared nothing clustering. In shared nothing clustering, each server in the cluster operates independently and has its own resources, such as storage and memory. Servers communicate with each other to coordinate tasks and share information. Benefits of clustering. High availability. Clustering provides high availability by ensuring that services remain accessible even if individual servers fail. Failover mechanisms automatically redirect client requests to healthy servers. Scalability. Clustering allows for horizontal scalability by adding more servers to the cluster to handle increased workload demand. Load balancing. Load balancing distributes client requests evenly across servers, preventing overloading of individual servers and improving overall system performance. Comparison. Replication focuses on data redundancy and read scalability, suitable for read-heavy workloads and improving fault tolerance. Asynchronous replication may introduce replication lag. Clustering focuses on high availability and workload distribution, suitable for ensuring continuous service availability and improving overall system scalability. Requires coordination and management of cluster resources and communication. In summary, replication and clustering are complementary techniques used to improve the availability, fault tolerance, and performance of database systems. Replication provides redundancy and read scalability, while clustering ensures high availability and workload distribution. The choice between replication and clustering depends on the specific requirements of the application, including workload characteristics, fault tolerance objectives, and scalability needs. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about database management system, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to my Advanced Database Management System course. In this section, we discuss about Redis in-memory data store data structures, pub/sub messaging, persistence, replication, and high availability. Let's enjoy. Redis is an open-source, in-memory data structure store that is commonly used as a NoSQL database, cache, and message broker. It is known for its speed, versatility, and simplicity, making it a popular choice for a wide range of use cases. Here's an overview of Redis. 1. In-memory data store. Redis stores data primarily in memory, allowing for extremely fast read and write operations. It also supports persistence options, such as snapshots and append-only files for data durability. 2. Data structures. Redis supports various data structures, including strings, hashes, lists, sets, sorted sets, bitmaps, and geospatial indexes. These data structures enable developers to model and manipulate complex data types easily. 3. Key value store. Redis follows a key value data model, where each data item, value, is associated with a unique identifier, key. This simple yet powerful model allows for efficient storage and retrieval of data. 4. Pub/sub messaging. Redis supports publish-subscribe messaging patterns, allowing clients to subscribe to channels and receive messages published to those channels in real time. This feature is commonly used for building real-time messaging systems, chat applications, and event-driven architectures. 5. Cache. Redis is often used as a cache due to its fast read and write speeds. It can store frequently accessed data in memory, reducing the need to retrieve data from slower disk-based databases or external systems. 6. Persistence. Redis offers different persistence options to ensure data durability. These options include snapshots, point-in-time backups, and append-only files, AOF, which log every write operation, enabling data recovery in case of system failures. 7. Replication and high availability. Redis supports master-slave replication, where data from a master node is asynchronously replicated to one or more slave nodes. This replication provides fault tolerance and high availability by allowing clients to read data from replicas in case the master node fails. 8. Lua scripting. Redis allows users to execute Lua scripts directly within the database engine. This feature enables developers to perform complex operations and transactions atomically, enhancing Redis's functionality and flexibility. 9. Redis modules. Redis supports modules, which are dynamic extensions that enhance its capabilities. These modules can add new data types, commands, and functionalities to Redis, allowing users to customize and extend its functionality as needed. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about Database Management System, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to my Advanced Database Management System course. In this section, we discuss about popular relational DBMS, Oracle Database, Microsoft SQL Server, PostgreSQL, SQLite, IBM DB2, MariaDB. Let's enjoy. Several relational database management systems, RDBMS, are widely used in the industry, each offering its own set of features, performance characteristics, and suitability for different use cases. Here are some of the most popular RDBMS. MySQL. MySQL is an open-source relational database management system that is widely used for web applications and small to medium-sized databases. It is known for its speed, reliability, and ease of use. MySQL is compatible with various operating systems and programming languages and is commonly used in conjunction Apache, MySQL, PHP, Stack. Oracle Database. Oracle Database is a commercial RDBMS developed by Oracle Corporation. It is one of the most powerful and widely used databases, particularly in enterprise environments. Oracle Database offers a wide range of features, including scalability, high availability, security, and advanced analytics capabilities. It is commonly used for mission-critical applications and large-scale data processing. Microsoft SQL Server. Microsoft SQL Server is a relational database management system developed by Microsoft. It is widely used in Windows-based environments and integrates closely with other Microsoft products such as .NET Framework and Microsoft Azure. SQL Server offers features such as high availability, business intelligence, and integration services, making it suitable for a wide range of applications, from small businesses to large enterprises. PostgreSQL. PostgreSQL is an open-source relational database management system known for its robustness, extensibility, and advanced features. It supports a wide range of SQL features, as well as features such as native support for JSON data, full-text search, and geospatial data processing. PostgreSQL is often used in web applications, data warehousing, and geographic information systems, GIS. SQLite. SQLite is a lightweight, serverless, self-contained, relational database engine that is embedded into applications. It is popular for use in mobile apps, desktop applications, and embedded systems due to its small footprint, simplicity, and ease of integration. SQLite databases are stored as single files, making them easy to deploy and manage. IBM DB2. IBM DB2 is a family of relational database management systems developed by IBM. It offers features such as high availability, performance optimization, and advanced analytics capabilities. DB2 is commonly used in enterprise environments for data warehousing, transaction processing, and business intelligence applications. MariaDB. MariaDB is an open-source fork of MySQL, developed by the original creators of MySQL. It is designed to be compatible with MySQL while offering additional features, performance improvements, and enhanced security. MariaDB is commonly used in web hosting environments, cloud platforms, and high-availability setups. These are some of the most popular relational database management systems used in various industries and applications. The choice of RDBMS depends on factors such as performance requirements, scalability, budget, and specific features needed for the application. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about Database Management System, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to Advanced Database Management System. In this section, we discuss about database type and various kind of database. What is a database and nature of database? Key characteristics of databases, database security and scalability. Let's enjoy. A database is an organized collection of data, typically stored and accessed electronically from a computer system. It's designed to efficiently manage, store, retrieve, and manipulate data according to various requirements and functionalities. Databases are essential components of modern information systems and are used across various industries and applications, including business, finance, healthcare, education, government, and more. They serve as repositories for structured, semi-structured, and unstructured data, allowing users and applications to store, retrieve, and manipulate data as needed. Key characteristics of databases include structured data. Databases organize data in a structured format, usually using tables, rows, and columns. This structure facilitates efficient storage, retrieval, and manipulation of data. Data integrity. Databases enforce data integrity rules to ensure the accuracy, consistency, and reliability of data. This includes enforcing constraints such as primary keys, foreign keys, and data types. Querying and retrieval. Databases provide query languages, example SQL for relational databases, or APIs, that allow users and applications to retrieve and manipulate data stored in the database. Concurrency control. Databases support concurrent access to data by multiple users or applications while ensuring data consistency and integrity through mechanisms such as transactions and locking. Security. Databases implement security measures to protect data from unauthorized, ensuring confidentiality, integrity, and availability. This includes user authentication, authorization, and encryption. Scalability. Databases are designed to scale to accommodate growing amounts of data and increasing numbers of users or transactions. Backup and recovery. Databases offer features for data backup and recovery to prevent data loss due to hardware failure, human error, or other unforeseen circumstances. This includes regular backups, point-in-time recovery. There are different types of databases, including relational databases, organize data into tables with predefined schemas and use structured query language, SQL, for querying and manipulation. Examples include PostgreSQL, MySQL, Oracle Database, and Microsoft SQL Server. NoSQL databases, designed for handling large volumes of unstructured or semi-structured data and provide flexible schemas. Examples include MongoDB, Cassandra, Redis, and Apache HBase. NewSQL databases combine elements of traditional relational databases with features for scalability and performance. Examples include Google Spanner and CockroachDB. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about Database Management System, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to Advanced Database Management System. In this section, we discuss about database type and various kind of database. Relational databases, RDBMS, NoSQL databases, in-memory databases, time series databases, spatial databases, object-oriented databases. Let's enjoy. Databases come in various types, each tailored to specific data storage and retrieval needs. Here are some common types of databases. Relational databases, RDBMS. Relational databases organize data into tables with rows and columns, and relationships between tables are defined by keys. They use structured query language, SQL, for querying and manipulating data. Examples include PostgreSQL, MySQL, Oracle Database, Microsoft SQL Server, and SQLite. Data analysis and insights. Databases serve as repositories for historical and transactional data, enabling organizations to perform in-depth analysis, generate reports, and extract valuable insights. By leveraging data analytics tools and techniques, businesses can uncover patterns, trends, and correlations that drive strategic decision-making and competitive advantage. Scalability and performance. Databases are designed to scale horizontally or vertically to accommodate growing volumes of data and increasing user demands. Whether it's adding more servers, optimizing query performance, or implementing caching mechanisms, databases provide scalability and performance features to ensure seamless operation and responsiveness. In-memory databases. In-memory databases store data primarily in system memory, RAM, rather than on disk, resulting in faster data access and retrieval. They are ideal for applications requiring high-speed data processing and low-latency access. Examples include Redis, Memcached, SAP HANA. In-memory databases. In-memory databases store data primarily in system memory, RAM, rather than on disk, resulting in faster data access and retrieval. They are ideal for applications requiring high-speed data processing and low-latency access. Examples include Redis, Memcached, SAP HANA. Time series databases. Time series databases are optimized for storing and querying time-stamped data points or measurements. They are commonly used in applications such as IoT, Internet of Things, monitoring systems, and financial analytics. Examples include InfluxDB, Prometheus, Graphite. Spatial databases. Spatial databases specialize in storing and querying geometric, geographic, or spatial data, such as maps, coordinates, and shapes. They provide spatial indexing and spatial querying capabilities for efficient spatial data management. Examples include PostGIS, extension for PostgreSQL, Oracle Spatial, MongoDB with GeoJSON support. Object-oriented databases, OODBMS. Object-oriented databases store data in the form of objects, similar to object-oriented programming languages. They support inheritance, encapsulation, and other object-oriented concepts. Examples include DB4O-DB. Wide column stores. Wide column stores are designed for storing and querying large volumes of data with high availability and scalability. Organize data into columns rather than rows, allowing for efficient storage and retrieval. Examples include Apache Cassandra, Google Bigtable. Each type of database has its advantages and use cases, and the choice depends on data structure, volume, performance requirements, scalability needs, and application-specific requirements. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about Database Management System, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to my Advanced Database Management System course. In this section, we discuss about overview of DBMS, data manipulation, data retrieval, data integrity, concurrency control, transaction management, security, backup and recovery, performance optimization. Let's enjoy. A database management system, DBMS, is software designed to facilitate the creation, organization, retrieval, management, and manipulation of data in a database. It serves as an interface between the database and end users or applications, providing mechanisms for data storage, querying, and administration. Here's an overview of the key components and functions of a DBMS. 1. Data definition. DBMS allows users to define the structure of the database schema, including tables, columns, data types, constraints, and relationships. It provides tools and languages such as SQL for creating, altering, and dropping database objects. 2. Data manipulation. DBMS supports operations for inserting, updating, deleting, and querying data stored in the database. Users can interact with the database through query languages, example SQL, or application programming interfaces, APIs, to perform various data manipulation tasks. 3. Data retrieval. DBMS enables users to retrieve and access data from the database using query languages like SQL. It supports filtering, sorting, and aggregating data to extract meaningful information from large datasets. 4. Data integrity. DBMS enforces data integrity by enforcing constraints, rules, and validations to ensure the accuracy, consistency, and reliability of data stored in the database. It prevents invalid or inconsistent data from being inserted or modified in the database. 5. Concurrency control. DBMS manages concurrent access to the database by multiple users or applications to ensure data consistency and isolation. It employs concurrency control techniques such as locking, timestamping, and multi-version concurrency control (MVCC) to coordinate access and maintain data integrity. 6. Transaction management. DBMS supports transactions, which are sequences of operations treated as a single logical unit of work. It ensures transactions are atomic, consistent, isolated, and durable, ACID, to preserve data integrity and recoverability in the event of failures. 7. Security. DBMS provides mechanisms for securing data and controlling access to the database. It supports authentication, authorization, and access control mechanisms to restrict unauthorized access and protect sensitive information from unauthorized users. 8. Backup and recovery. DBMS facilitates backup and recovery operations to safeguard against data loss and corruption. It allows users to perform database backups, restore operations, and recovery procedures to recover data in case of disasters or system failures. 9. Performance optimization. DBMS optimizes database performance by implementing indexing, query optimization, caching, and storage optimization techniques. It aims to minimize query execution time, reduce resource utilization, and improve overall system efficiency. 10. Administration and monitoring. DBMS provides tools and utilities for database administration, monitoring, and maintenance tasks. It allows administrators to manage database configurations, monitor performance metrics, diagnose issues, and tune system parameters to ensure optimal database operation. Overall, a DBMS serves as a foundational component of modern information systems, providing essential functionality for storing, managing, and accessing data efficiently and securely. It plays a crucial role in enabling organizations to leverage their data assets effectively and make informed business decisions. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about Database Management System, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to my Advanced Database Management System course. In this section, we discuss about best practices for securing databases, strong authentication, patch management, auditing and logging, data masking and anonymization, database activity monitoring, DAM. Let's enjoy. Securing databases is essential for protecting sensitive data, ensuring data integrity, and maintaining regulatory compliance. Here are some best practices for securing databases. 1. Strong authentication. Implement strong authentication mechanisms, such as multi-factor authentication, MFA, to verify the identities of users accessing the database. Enforce the use of complex passwords, regularly rotate passwords to prevent unauthorized access. 2. Role-based access control. Use role-based access control (RBAC) to enforce the principle of least privilege. Assign permissions to roles based on job responsibilities and limit access to sensitive data to only those users who require it for their work. 3. Encryption. Encrypt data at rest and in transit to protect it from unauthorized access and data breaches. Use encryption techniques such as transparent data encryption (TDE), so data at rest and secure sockets layer, transport layer security (SSL), TLS for data in transit. 4. Patch management. Regularly apply security patches and updates to the database management system (DBMS) and underlying system to address known vulnerabilities and security issues. Establish a patch management process to ensure timely deployment of patches. 5. Auditing and logging. Enable auditing and logging features in the DBMS to track database activities, including user logins, access, and data modifications. Monitor regularly for suspicious activity and access attempts. 6. Data anonymization. Mask sensitive data in non-production environments to prevent unauthorized and maintain data privacy. Use data anonymization techniques to replace personally identifiable information (PII) with fictitious or obfuscated data. 7. Database activity monitoring (DA). Implement database activity monitoring (DA) to continuously monitor database traffic and detect anomalies, attempts, and security threats in real time. Set up notifications for suspicious activity. 8. Regular security audits. Conduct regular security audits and assessments of the database infrastructure to identify security vulnerabilities, and compliance gaps. Use automated scanning manual techniques to assess security posture comprehensively. 9. Data backup and disaster recovery. Implement and disasters and business in the event corruption. Regularly test recovery procedures by their effectiveness. 10. Employee security training programs, base administrators, developers, and other about practices, policies, and procedures. Raise awareness about common security threats and social engineering techniques. 11. Vendor and third-party risk management. Assess the security posture of third-party vendors and service providers that have access to the database or handle sensitive data. Establish security requirements and contractual obligations to ensure compliance with security standards. 12. Data retention and disposal. Implement data retention and disposal policies to securely manage the lifecycle of data stored in the database. Regularly review and purge outdated or unnecessary data to minimize the risk of unauthorized access and data breaches. By following these best practices, organizations can strengthen the security of their databases, mitigate the risk of data breaches and compliance violations, and protect sensitive information from unauthorized access and misuse. Additionally, it's important to inform threats and security trends to adapt security measures accordingly and maintain an effective defense posture. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about database management system, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to my advanced in this section, entities, properties or attributes, types of entities, associative entities, granularity. Let's enjoy. Entities, text of ownership. model databases, real-world objects or concepts about which data needs to be stored. They are the building blocks of a database schema and are used to organize and classify data. Each entity typically corresponds to a table in a relational database. Here's a more detailed explanation of entities. Characteristics of entities: real-world objects or concepts. Entities represent tangible or intangible objects, concepts, or events in the real world that are relevant to the domain being modeled. Unique identity. Each entity must have a unique identifier attribute or set of attributes that distinguishes one instance of the entity from another. This identifier is often referred to as the primary key in a database table. Properties or attributes. Entities have properties or attributes that describe their characteristics or qualities. Attributes define the data elements associated with an entity and provide details about the entity's features. Examples of attributes for an employee entity might include ID, first name, last name, date of birth, etc. Relationships. Entities can have relationships with other entities, representing associations or interactions between them. Relationships define how entities are connected or linked to each other, and specify the cardinality and participation constraints. Types of entities. Strong entities. Strong entities have their own unique identifiers and can exist independently of other entities. They are represented by standalone tables. Examples: employee, customer, product. Weak entities. Weak entities do not have sufficient attributes to uniquely identify them without considering their relationship with another entity. They depend on the existence of a related entity, known as the owner entity. For identification, weak entities are typically represented by tables that have a one-to-many relationship with their owner entities. Examples: order item depends on order, dependent depends on employee. Associative entities. Associative entities, also known as intersection entities or many-to-many entities, represent relationships between two or more entities. They are used to resolve many-to-many relationships into one-to-many relationships. Associative entities are often implemented as separate tables that contain the primary keys of the entities involved in the relationship. Examples: order item, associative entity between order and product. Student course, associative entity between student and course. Design consideration, relevance to domain. Entities should be defined based on their relevance to the domain being modeled and the requirements of the database. Granularity. Entities should be defined at an appropriate level of granularity, balancing the need for detailed data capture with simplicity and manageability. Normalization. Entities should be normalized to eliminate redundancy and ensure data integrity, following the principles of database normalization. Entities play a fundamental role in modeling and database design. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about database management system, the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to my Advanced Database course. In this section, we discuss about entity relationship, modeling, key components of modeling, attribute, relationship, cardinality, and multiplicity. Steps in modeling. Create diagram. Let's enjoy. Entity relationship modeling is a conceptual modeling technique used in software engineering and database design to visually represent the entities, attributes, and relationships between them within a domain of interest. It helps in understanding the structure of the data and the relationships between different entities in a system. ER modeling is typically used during the initial stages of database design to capture requirements and establish a blueprint for the database schema. Key components of ER modeling. Entity. An entity represents a real-world object, concept, or thing that is relevant to the system being modeled. Entities are depicted as rectangles in an ER diagram and are labeled with singular nouns. Example: customer, product, employee. Attribute. Attributes are the properties or characteristics of entities that describe them. Each entity has one or more attributes, which are represented as ovals in an ER diagram and are labeled with descriptive names. Example: customer ID, first name, last name. Relationship. Relationships represent the associations or connections between entities. They describe how entities interact or relate to each other within the system. Relationships are depicted as lines connecting entities in an ER diagram and are labeled with verbs or verb phrases. Example: orders, manages, owns. Cardinality and multiplicity. Cardinality defines the number of instances of one entity that can be associated with the number of instances of another entity through a relationship. It specifies the minimum number of occurrences allowed in a relationship. Example: 1-to-1, 1-to-1, 1-to-many, 1-to-many, many-to-many. A primary key is a unique identifier for each instance of an entity. It uniquely identifies each record within the entity and is used to establish relationships with other entities. In ER diagrams, primary keys are typically underlined or otherwise indicated. Steps in ER modeling. Identify entities. Identify the main entities or objects of interest within the system being modeled. These are typically nouns that represent real-world entities. Define attributes. Determine the properties or attributes of each entity. These describe the characteristics of the entities and are typically represented as fields in a database table. Establish relationships. Identify the relationships between entities. Determine how entities are related to each other and specify the cardinality and multiplicity of each relationship. Refine model. Refine the ER model by adding additional details, such as constraints, business rules, and additional entities or relationships as needed. Create ER diagram. Create an ER diagram to visually represent the entities, attributes, and relationships identified in the model. The diagram provides a clear and concise overview of the data structure and relationships within the system. ER modeling provides a systematic approach to database design, allowing designers to capture the requirements of the system and create a blueprint for the database schema. It helps in ensuring data integrity, reducing redundancy, and establishing clear relationships between entities, ultimately leading to a well-structured and efficient database design. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about Database Management System, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to Advanced Database Management System. In this section, we discuss about relational databases. Key characteristics of relational databases: data integrity, normalization, structured query language, SQL, ACID properties, advantages of relational databases. Let's enjoy. A relational database is a type of database management system, DBMS, organizes and stores data in a tabular format, with between data represented by shared keys or common attributes. It follows the relational model proposed by Edgar F. Codd in 1970, which defines data in terms of rows, columns, and tables, with each table having a unique name and containing related data. Key characteristics of relational databases: tabular structure. Data in a relational database is organized into tables, with each table consisting of rows, also known as tuples or records, and columns, also known as attributes or fields. Each row represents a single record or data instance, and each column represents a specific data attribute. Relationships. Relational databases support relationships between tables through keys or common attributes. Primary keys uniquely identify each row within a table, while foreign keys establish relationships by referencing the primary key of another table. Data integrity. Relational databases enforce data integrity constraints to maintain the accuracy and consistency of data. This includes primary key constraints to enforce uniqueness, foreign key constraints to ensure referential integrity, and other constraints such as check constraints to enforce data validity. Normalization. Relational databases typically undergo a process called normalization to organize data and eliminate redundancy. Normalization involves breaking down tables into smaller, more manageable components to reduce data duplication and dependency, thereby improving data integrity and database efficiency. Structured Query Language (SQL). Relational databases use a standardized language, structured query language (SQL), for querying, manipulating, and managing data. SQL provides a rich set of commands and operations for creating, modifying, and querying relational databases. ACID properties. Relational databases adhere to the principles of ACID, atomicity, consistency, isolation, durability, to ensure transactional reliability and data integrity. ACID properties guarantee that database transactions are executed reliably and consistently, even in the event of system failures or errors. Advantages of relational databases. Flexibility. Relational databases offer flexibility in data modeling and querying, allowing users to define and manipulate data structures according to their requirements. Scalability. Relational databases can scale to accommodate large volumes of data and support growing user loads through features such as sharding, replication, and clustering. Security. Relational databases provide robust security features such as user authentication, access control, and encryption to protect sensitive data from unauthorized access and breaches. Interoperability. Relational databases support standardized SQL interfaces, making it easier to integrate with various applications, tools, and platforms. Examples of relational database systems: MySQL, PostgreSQL, Oracle Database, Microsoft SQL Server, SQLite, IBM DB2. In summary, relational databases offer a powerful and flexible solution for storing, managing, and querying structured data. They provide a standardized and reliable approach to data management, making them widely used in various applications across industries. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about data management system, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to Advanced Database Management System. In this section, we discuss about database, table creation. Let's enjoy. Create table employees. Employee ID in primary key. First name, varchar 50. Last name, varchar 50. Email, varchar 100. Department ID int, hire date. Constraint FK department employees. Foreign key, department ID references department's department ID. End. Explanation of the above code. Create table employees. This line starts the creation of a new table named employee ID int primary key. This line defines a column named employee ID of type int integer as the primary key for the table. Primary keys uniquely identify each row in the table. First name, varchar 50. This line defines a column named first name of type varchar, variable length character string, with a maximum length D characters. Last name, varchar 50. This line defines a column named last name of type varchar, with a maximum length of 50 characters. Email, varchar 100. This line defines a column named email of type varchar with a maximum length of 100 characters. Department ID, int. This line defines a column named department ID of type int to store the department ID of the employee. Hire date, date. This line defines a column named hire date of type date to store the date when the employee was hired. Constraint, FK department employees, foreign key department ID references department's department ID. This line defines a foreign key constraint named FK department employees that references the department ID column in the department's table. This ensures referential integrity by ensuring that each department ID in the employees table must exist in the department's table. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about Database Management System, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to Advanced Database Management System. In this section, we discuss about rows, records, tuples. Let's enjoy. Example table structure. Create table my table. ID int, primary key, name varchar, age inserting into my table. ID, name, age, values 1, John 30. Multiple rows at once into my table. ID, name, age. In this Alice structure
3,
of the table,
Bob,
my
35,
table, with
4,
columns
Charlie,
ID 40, name, and age. Insert a single row into the table with values 1, John 30. We also insert multiple rows at once using a single insert into statement. Each row is enclosed within parentheses and separated by commas. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about Database Management System, please check the next. Never stop learning. Thanks once again to enjoy the lesson. Welcome to Advanced Database Management System. In this section, we discuss about columns, attributes, data types, constraints, indexing, normalization, query, and retrieval. Let's enjoy. In the context of database, columns refer structures within a table where data is each a specific author. Columns in databases. Columns different attributes of the models. In a database, you might such as first name and date. Each column type which define data in that column. Common data types include integers, strings, text, dates, floating point numbers, and more complex types like blobs, binary large objects, for storing images or documents. Constraints. Columns can have constraints applied to them, which enforce rules or conditions on the data stored within them. Common constraints include primary keys, foreign keys, unique constraints, and check constraints. Indexing. Columns can be indexed to improve the performance of queries that involve searching or sorting based on the values in those columns. Indexes provide a faster way to retrieve data by creating a sorted list of values for a particular column. Normalization. Columns play a crucial role in the normalization process of database design. Normalization involves organizing the data in a database to minimize redundancy and dependency, typically by breaking larger tables into smaller ones and ensure them represents a single piece of information. Queries and retrieval. When querying a database, columns are used to specify which attributes of the data you want to retrieve or manipulate. SQL, structured query language, is commonly used to interact with database, allowing you to operate column on column values and aggregating data across columns. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about database management system, please check the next lesson. Never stop learning. Once again, to enjoy the lesson. Welcome to Advanced Database Management System. In this section, we discuss about primary keys and foreign keys. Let's enjoy. Keys, specifically and foreign keys, are crucial to relational database design. They establish relationships between tables and ensure data integrity. Here's an explanation of primary keys and foreign keys. Primary key. A primary key is a column or a set of columns in a table that uniquely identifies each record in the table. It must have a unique value for each row, and it cannot contain null values. Primary keys are defined when creating the table using the primary key constraint. By default, primary keys also typically have an associated index for fast data retrieval. Example, in a table of employees, the employee ID column could be designated as the primary key. Foreign key. A foreign key is a column or a set of columns in one table that establishes a link to a primary key in another table. It represents a relationship between two tables, where the values in the foreign key column table match the values in the primary key. Foreign keys in integrity, ensuring that values in the referencing table column list in the referenced table's primary keys are defined using the foreign key constraint. Example is a foreign key referencing the customer in the customer relationship and create table employees. Employee ID int primary key first name varchar 50.